variance, standard deviation. Here, the focus is on statistical inference or inferential statistics. So we have descriptive statistics, we have inferential statistics. With descriptive statistics, we describe large data sets with one or two values. With inferential statistics, the goal is to make inferences, right? Is to draw conclusions from data. And then the second part is the conclusions we are drawing from the data. How confident are we in those conclusions? So that's the goal in inferential statistics. Draw conclusions from data and quantify the confidence you have in those conclusions. So the focus is on the uncertainty in the statements we make about the variations in the limited data sample we have. Why? Because we will never have, in most cases, you will never have all of the population. You always work with samples, so you need to be able to come up with some quantification of the uncertainty you have in whatever statistical estimate you've made. So here I give an example that you might be interested in extrasolar planets. And then you have some sample, right, of if some of the planets you have in our galaxy. You never know them all, right? Every year, every now and then, they keep updating the number of planets we have. So if you use all of the planets we have observed today, would that be representative of the entire population? Here we are making a point that actually it may not be. More likely than not, whatever our sample is will not be representative. Why? Because the bigger planets are the easier ones to observe. So you have a tendency to oversample the large planets. The ones that are so small, you need more resolution technologies to be able to see them, to observe them. So whenever we work with samples, it's not useful to just give an estimate. We need to know the confidence we have in those estimates. And that is extremely important. We saw some of those within the context of the effectiveness of certain drugs to the COVID-19 at the beginning. So the tests were made on a few select samples, like 100 people or 200, whatever number of people. And then they will say from the statistics we've observed based on the sample, it looks like this drug works against COVID-19. First, it was some chloroquine kind of stuff, and then it was remdesivir. And then you'll hear, sometimes you don't hear anything about the confidence in the statistical inference, and that's the important point. In some cases, you'll hear something like a p-value. The p-value indicates the level of confidence. So that's very important. So just saying something appears to work is not useful. You need to be able to quantify the level of confidence you have in the estimate. And that's what we do with confidence interval. So with confidence interval, we quantify the interval using a range. So to get 95% in the middle of a normal distribution, for instance, you will have 2.5% on the left and to the right. And all of this will make more sense once we go into the Python lab. So you will see exactly how we calculate this confidence interval. If this is a normal distribution, we actually talked about it that about 95% of your data will be within how many standard deviations? 68.5 thereabouts will be within one standard deviation. This is the middle. We said one standard deviation, you have about 68% of the data between these two lines I just did here. One standard deviation. Two standard deviations, you actually have about 95% of your data in this interval for a normal distribution. So if the statistics, whatever we are doing, it looks like a normal distribution, then you know this is 95% of your data here, this interval. And now what does that mean? It means you only have 2.5% here, right? And another 2.5% here because it's symmetric. So if you can bracket whatever statistics you're measuring to be within this interval, then you can say for a fact that 95%, there is 95% chance that whatever conclusions you are drawing is true. That will mean if it's like for an election, if you conduct the election 100 times, 95% out of the 100 times, whatever we predict, whoever will predict will be the winner will be the winner. And that's what we do with p-values. With p-values, we focus on this guy. So p-values, you want it to be less than 5%. So if they tell you that remdesivir works and the p-value is 7, you already know that's useless. If they tell you it works and they don't tell you the p-value, it's also useless, right? If they tell you it works and then the p-value is 1% or 0.005 or something very small, then you know there is a high confidence based on the sample that it works. And why is this important? It's important because you never have the population. So if any conclusion you make based on the sample, you will really need to be able to evaluate the level of certainty you have in the conclusions. And that's the whole purpose of statistical inference, drawing conclusions and putting a number on the level of confidence you have in those conclusions. So here, I say we can say 95% of the time the range will include the true value, and that will mean 95 percentile. So that's basically what I've explained here, these first 2 points. 95% of the times means that if we're to make polls in 100 elections and compute the confidence interval for each election, then for approximately 95 of those, the intervals will include the true value. You will not know which one is not including the true value, but 95% is pretty good enough. Bootstrapping. This is a powerful concept that was introduced in 1979. All of this, the previous slide and this slide is focusing on the weakness of using a sample, which is probably what you will use almost all the time. You never have the full population. But what bootstrapping tries to account for is what could have happened. So if you do a test on 100 patients and you obtain a certain result, Bootstrap is saying, yeah, that is a specific realization because this is statistics. Nothing is certain. There is some uncertainty. You could have got a different result if you had picked a different group of 100 people. So bootstrapping will resample from the sample without replacement. Does that make any sense? This is how that works. If you have 10, let's say we have only 10 samples, which is ridiculous. You're not going to get useful statistics from 10 people. And then you want to figure out what would have happened. So let's assume the result we're testing is 0 or 1. Do they react positively or negatively? What bootstrapping does is it's going to create multiple realizations of this from this same one, that we all have the same length with this. But of course, it's not going to be identical. You could have had a 1 if you had used a different patient in place of this. You could have had a 1 here, but we want to have the same kind of mean, the same kind of variance. So what do we do? Any ideas of how to get a list of the same length from the previous one? We will see this in code. So for those of you online, if you can't see my sketch, I'll try to bend it towards it. If you can't see, that's fine. We're going to see examples. So we need multiple of these of the same length, but we want them to be different realizations, which would indicate what could have happened. This is what happened based on the sample, but it's just a sample. If you got a different sample, you could have obtained a different result. So what we do to fill up this as many times as you want is what? Sampling with replacement. So what does that mean? Pick a random index out of this 10. Let's say 7. So go to the 7th item, grab that 7th item, put it here. It's replacement because we put the 7 back. We'll never change this list. And then generate another random index. What if it's 7 again? That's fine. We'll put the 7 here. Generate another random index. If it's 3, go grab the third item. Oh, it's 1. Generate another random number. It's 2. Okay, it's 0. And you do that until you fill up the length. And you keep doing that over and over and over and over again. So you can actually create multiple realizations from one realization. And that is bootstrapping. So you see, these things have powerful names, but the names sound complex, but they're very simple. Bootstrapping just means sampling with replacement. And then after you sample with replacement, now what can you do? You can find the mean of all of these 100 stuff, right? And when you start to have multiple realizations, then you know you can come up with this, right? Because multiple numbers, that's exactly what you do with probabilistic distribution. And once you can come up with this, then you can grab the 2.5th percentile, 97.5th percentile, and then you can come up with the confidence interval. So that's the power of bootstrapping. It allows us to evaluate all the possible outcomes given a limited sample. It's based on resampling the data. So it's just sampling with replacements. And then you can compute the mean of those resampled data sets. We then compute inferential statistics using the percentiles, right? And bootstrapping requires that that original sample is representative. So if the first sample is not representative and you are resampling that, that's not going to lead us anywhere, right? And there is actually some complicated mathematics that show some lemmas proving that it works. But we are not interested in those in this course. We just want to use it. And this is a precise process that I'm going to show in the lab. So I'm not going to talk much on this, but just know that the null hypothesis is going to involve these 3 steps. And you can come back and look at these 3 steps when we actually see an example in code for this. Any questions on inferential statistics? So I can set up multiple choice problems and describe a scenario where maybe we are making conclusions from data and ask whether it's inferential or descriptive statistics. Inferential, inference. So you're drawing an inference, you're drawing conclusions from data, that's inferential statistics. You are describing, you're summarizing, that's descriptive statistics. Like mean, median, mode, those are under descriptive statistics. Drawing conclusions, those are under statistical inference or inferential statistics. And I said, just drawing conclusions and not commenting on the confidence you have in the conclusions is useless. And that's what happens a lot in the media these days. People give numbers and then they don't tell you what the confidence of interval is. That number is meaningless in itself. Because if the confidence interval is 50%, then you can really push any agenda you want to push using those. So very important to pay attention to confidence intervals. And we're going to do those in the labs and you see exactly how to calculate it. And then very important to understand what those p-values mean. So when someone gives you what the p-value is, you should know whether that's something that they have a lot of confidence on or they don't. And all of this is very important because we deal with samples. We never get access to the full population. And we are still able to make useful conclusions from the samples using bootstrapping, which is just resampling with replacements.